Welcome to this lecture. Today we are going to discuss about classical and quantum statistics. So, what are classical and quantum statistics? So, particles can be divided into two categories. One are the classical particles, another is the quantum particles. Okay. So, what is the difference between these two particles? How can we distinguish between them? So, usually classical particles are considered to be distinguishable, whereas quantum particles are indistinguishable. Okay, so next, this cannot be the proper basis of distinction between classical and quantum particles, because in Gibbs paradox we have seen that to resolve the paradox, the classical particles were considered to be indistinguishable. So one more parameter can be the degeneracy factor. So what is this degeneracy factor? This is given by n lambda cube, and if it is very less than 1, then this is degenerate case. Okay, and if it is nearly equal to 1, this is the quantum case, and if it is very greater than 1, then this is the classical non-degenerate case. Okay, so another way is the de Broglie wavelength. Okay, so if the de Broglie wavelength is very less than the size of the particle, then these are considered as classical particles, and if it is comparable to the size of particles, then these are the quantum particles. Next way is the spin of the particles. So based on the spin, again the classical particles do not have any spin, but based on the spin, the quantum particles are again differentiated into two types. One is the fermions, another is the bosons. So fermions have half integral spin, for example, half, 3 by 2, 5 by 2, and so on. And bosons will have integral spin, for example, 0, 1, 2, and so on. Okay. So now there is no restriction on filling the boson particles in different energy levels. Okay. So this you can fill any number of particles in one energy level in case of bosons, but for fermions we have some restrictions. Okay, so fermions have lots of tantrums, so they don't want a similar kind of particle, they don't want to be with similar kind of particle in a same energy level. So and these restrictions are given by the Pauli's exclusion principle. So according to the Pauli's exclusion principle, two particles having the same intrinsic properties cannot be in the same energy level. So what are the intrinsic properties? These are the spin, mass, and charge. Okay. So if any one of these is different, then two particles, maximum two particles can be in one energy level. But if all of these are same, then they cannot be in the same energy level. Okay. So now we use classical statistics to study the classical particles and quantum statistics to study the quantum particles. So for classical particles, we have Maxwell-Boltzmann statistics. Since classical particles were found by Maxwell, and the statistics to study this particle was given by Boltzmann. And for fermions, we have the Fermi-Dirac statistics. Since these particles were found by Fermi, and the statistics was given by Dirac. And for bosons, we have the Bose-Einstein statistics. Since these particles were found by Bose, and the statistics was given by Einstein. Okay. So next, most probable macrostate distribution and microstates for different statistics. Okay, so let's say we have Maxwell-Boltzmann statistics, Fermi-Dirac statistics, and Bose-Einstein statistics. Okay, so the most probable macrostate distribution, that is Ni, for Maxwell-Boltzmann statistics will be given by 1 upon e to the power minus alpha plus beta ei. Okay, for Fermi-Dirac statistics, this will be equal to 1 upon e to the power minus alpha plus beta ei plus 1, and for Bose-Einstein this will be equal to 1 upon e to the power minus alpha plus beta ei minus 1. Next, the microstate for the different statistics is given by, for Maxwell-Boltzmann, this is, we have many different formulas. So the most general one is m factorial pi I gi to the power ni upon ni factorial. Okay, so if we have only, so this is for n number of particles, and otherwise we can use this formula also without considering the spin, and if we have to consider the spin of particles, then we can use this formula. So for Fermi-Dirac statistics, the microstate is, number of microstates is given by gi factorial upon ni factorial and gi minus ni factorial. Okay, and product of this, and for here the microstates is given by ni plus gi minus 1 factorial upon ni factorial and gi minus 1 factorial. Okay, so we have to take the product. So next we have distribution function or probability of occupation. Okay, so the distribution function is given by f of e is equal to ni upon gi, which is equal to 1 upon e to the power minus alpha plus beta ei plus a. Okay, so a is equal to 0 for Maxwell-Boltzmann statistics, plus 1 for Fermi-Dirac statistics, and minus 1 for Bose-Einstein statistics. So we have already seen this. Then the chemical potential for Fermi-Dirac statistics is either positive or negative. For Bose-Einstein statistics, this is either 0 or negative, and for Maxwell-Boltzmann statistics, this is more negative. Okay, then the number of states in terms of energy and range. Okay, so the density of states is given by GeDE. Then the number of particles is given by integration 0 to infinity f of e GeDE, and the energy, total energy, is given by integration 0 to infinity e f of e GeDE. Okay, so next let's see some of the questions based on today's lecture. So given for a system of two bosons, okay, each of which can occupy any of the two energy levels 0 and E, the mean energy of the system at temperature T. Okay, so first of all, let's see how to arrange particles in different statistics. Okay, so let's take an example that we have to fill, say, two particles in three energy levels. Okay, so for Maxwell-Boltzmann, that is distinguishable particles, we can label the particles as AB. Okay, and so we have these three energy levels, E1, E2 and E3. Okay, so we can put A here and B here, or we can put A here and B here, or we can put A here and B here. Okay, so next we can put B here and A here, or B here and A here, right? Or B here and A here. Okay, so next we can also put all the two particles in the same energy level. Okay, so how many different types of distribution are you getting? Total 9, right? But if we consider for Bose-Einstein statistics, okay, so let's say these are our energy levels, E1, E2 and E3. So here particles will be indistinguishable. So one particle can be here and the next here, or one particle can be here and the next here, or one particle can be here and the next in this energy level, or both the particles can be in the same energy level. Okay, so how many different distributions you're getting here? 6, right? And in Fermi-Dirac statistics, here also the particles are indistinguishable. So let's say these are our 3 energy levels. Okay, so we can put one particle here and the next here. Since these particles will obey Pauli exclusion principles, we cannot put two particles in the same energy level. Okay, unless it is mentioned that it is a spin half particle or electrons. Okay, so let's say one particle we're putting here and the next in this energy level, or we can put one particle in this energy level and next in this energy level. So total we are having 3 distributions, right?